Well, we've seen a couple of situations now where we've actually been able to come up to an angle whose value is equal to square root of 3 over 2. Specifically, there's two angles in the plane that make this true. Sine of pi over 3 is radical 3 over 2, and that's based on our special right triangles. But the sine of 2 pi over 3 is also radical 3 over 2, and we ask, well, how can that be? Well, in fact, because it corresponds to right triangles that fall in quadrants where the sign is positive. And you'll recall, we were just looking at a diagram before. Let's try that again. We were looking at a diagram before where when we drew our right triangle containing pi over 3 in the first quadrant, we had a positive opposite side. The hypotenuse is always considered a positive value. And then when we went to 2 pi over 3, even though we were in the second quadrant, our opposite side and hypotenuse are also positive. That is because all students take calculus. Sine is positive in quadrants 1 and 2. So we're going to use that to our advantage. With the sine of 2 pi over 3 as a reference angle, right, we consider it this way, that the sine of radical, if we take radical 3 over 2 to 1, as we would in the unit circle, we would find that we got positive radical 3 over 2 over here in the second quadrant because this reference angle over here is contained in a right triangle that also contains pi over 3. Now, because it's sine, that's important. In sine, we don't care that the adjacent side is positive 1/2 and that the adjacent side over here for 2 pi over 3 is negative 1/2. Since both of these are positive, then we can say that 2 pi over 3 and pi over 3 are two angles whose sine is radical 3 over 2. So we might actually see a question that looks like this. Specifically, we might say, well, all right, if sine of some angle theta is equal to square root of 3 over 2, we might be asked to find two angles on the interval from 0 to 2 pi that give us this value. And of course, the answer is going to be, well, the two angles are pi over 3 and 2 pi over 3. All right. Well, I've illustrated this example right here, but all right, what happens if we don't know what's going on first? Let's start out with this one. Let's find two angles in standard position whose sine is square root of 2 over 2. All right, so we're saying that there's some angle sine of theta, some angle theta, whose sine is equal to positive square root of 2 over 2. So we would ask ourselves the question, in what quadrants is sine positive? Well, quadrant 1 is certainly a place where sine is positive, and quadrant 2 is the other quadrant. So let's proceed. If we are dealing with degrees, what do we know? Well, I know that based on my special right triangles that the sine of 45 degrees does indeed give me square root of 2 over 2. So I'm going to make my reference angle, theta prime, equal to 45 degrees. Okay. In quadrant 1, the angle whose sine would be radical 2 over 2 would also be 45 degrees. Quadrant 2, however, we're going to have to do a little bit of extra work. Because we're in quadrant 2, to get the angle we want, we're going to take 180 degrees, and we're going to subtract that 45 degrees, and we're going to find that the angle whose sine would be positive radical 2 over 2 will be 135 degrees. So our two angles are 45 and 135 degrees. All right, let's ask the question radians this time. Same thing, right? We know that based on our basic right triangles that the sine of pi over 4 is also equal to square root of 2 over 2. And that makes our reference angle also pi over 4. And as stated, this falls in quadrants 1 and 2. So in quadrant 1, the angle we want is pi over 4 radians. And in quadrant 2, the angle that we're going to want is pi minus pi over 4. And working that out gives me 3 pi over 4 as my other angle. That's what I wanted. So we're done.